Hello everyone, welcome to my Calc 3 videos. And today we're going to talk about gradient vector and directional derivatives. So let's start with some conceptual questions, right? Let's talk about gradients first. So what is the definition of a gradient? Well, I think everybody can easily agree that this will look like gradient of f is going to be partial f, partial x, and then partial f, partial y if it's a two variable case, and then we also have partial f, partial z if it's three variable case. It's a scalar or vector, right? It's a scalar. Oh, sorry. My bad, this is a vector, sorry. And what does it mean, right? So I think of it, the gradient is kind of like the 3D version or 2D version of the derivative that you have learned in Calc 1 and Calc 2. Right? It's instead of a scalar, now it's a vector, and it's pointing in a 3D direction. Right? It's a vector, so it has a direction, and then the direction is the maximum rate of change. Right? So it's similar. I wouldn't say analogous to direction, a direct derivative, right? Right, it's talking about rate of change. Right, so let's talk about directional derivatives. Once we have understood what gradient is. So the definition of directional derivatives. So I'm gonna go back to my notes, and here you go. So this is the 2D case. And this is, this is a 2D case, and this is the 3D case. And these are, and then let me go ahead and open my slides as well, right? So I just showed you the definition of directional derivative. So switch orientation, right? So here you go. There you go. Which vector product do you use, right? So is it a cross product or it's a dot product, right? It's a dot product, right? We're going to compute the dot product to get to our directional derivatives. And then there's a special requirement of the u vector, direction vector. It has to be a unit vector, okay? It cannot be any other vectors other than a unit vector. Right. So what is the meaning of directional derivatives? So we know that the gradient, right? The gradient is the maximum rate of change. So if you take a dot product with another directional vector, so for example, I have let's say my maximum rate of change is going in this direction, right? But this is my gradient of f, and then this is my unit vector, right? This is my direction vector. So what this does is it's going to the result is it's going to be a scalar quantity that tells us how much I will be ascending, or how much value will be increasing in the direction of u, right? It's kind of like, it's similar to now I think of it, it's kind of like the idea of projections, but you can go, but the unit vector can be any directions. So let me put a projection down right here, right? So this pink solid line will be the result of the directional derivative, and that will be the rate of change in the direction of u. So in that way you can. So the idea is you can calculate the rate of change at a particular point in any directions. It doesn't have to be the direction of the maximum rate of change. You can compute the rate of change at any directions as long as it's a unit vector. So using the property of dot product, right, how can we find the direction and magnitude of maximum and minimum rate of change? So using this example, right, so of course, the gradient of f itself represents the maximum rate of change, right? But, so that means if we go in the opposite direction, it would mean it's the minimum rate of change, or we call them steepest ascent and the steepest descent. So that is the idea between the two. So, right, I'm going to use this example of isobars, right? This is a pressure map. This is a pressure map, and then, so tell me, where are the gradients that will be the greatest? And that where on this isobar or on this pressure map has the greatest strongest gradient, right? So if there's a region of high gradient, that means the value of the function will be changing very rapidly, right? So that means these iso lines will be packed together, indicating a large change over a small distance. So I would say somewhere over here, right, has the gradient, strongest gradient, and somewhere maybe over here in the South America will have and over the Indian Ocean would have the smallest gradients, because the lines are not, the values are changing very slowly. So just continue to illustrate that idea a bit more. Let's go ahead and open Windy again. So this is the current pressure map, right? Just as we have seen before. So you can see that over like Indiana, Ohio, we have a tightly packed pressure isolines, and you can see these fluid animation particles are moving fairly quickly, right? As compared to, let's say, Texas, Oklahoma, those regions down the south, right? These tightly, and where these regions, they don't have many isolines packed closely together. That means there's a small gradient, things are changing very slowly, therefore we have slow moving air. Whereas in the Midwest, right now, right, we have like 10 knots of wind, maybe here we have like 4 knots of wind, right? So that is the idea, right? So larger the gradients, the more tightly packed isolines, and then then things can change more rapidly. So let's go ahead and do some real problems, real past exam problems. So we are at 15.5. Let's open the one-pager. Let's open the worksheet. So let the function be as such, and the direction of the steepest descent at the 2.3 is in the direction of the vector, right? So here's my question for you. What type of question is this, right? Is it, well, you might just by instinct to say, well, it's a gradient problem because we're talking about gradient, right? But what if I just throw a random question at you? How do you know this is the gradient problem, right? So again, let's investigate some keywords that can tell us that what type of question is this, right? So the biggest giveaway in this question will be the direction of steepest descent, right? So anytime you hear about the words descent, ascent, right? That tells that has something about rate of change. Rate of change in terms of values. So this is a gradient of the function problem, and then we have, let's say, steepest, maximum, minimum, ascent, descent, right? These are the words describing rate of change, right? Rate of change. So that tells us this is a gradient problem. So if it's a gradient problem, we're going to find the gradient, right? So therefore, naturally, this is the first step. First step is, so find the partial derivatives, right? So we have the function f equals to xy e xy. Oh, this is not a very fun derivative to do, partial derivative to do. So fx equals to 1 times y e x y plus x times y2 e x y equals to y plus x y squared e x y. I'm using the product rule right here. So f y equals to 1 times x e x y plus y times x squared e x y equals to x plus y x squared e x y. So therefore, since this is a two-variable function, equals to fx fy equals to, I'm just going to copy and paste. There you go. So this is the gradient of the function. Step 1 is complete. So step 2 is we're going to plug in the point into the gradient that we just have arrived to get the maximum rate of change. So this will be the steepest ascent, okay? Steepest ascent. But if we want to get the steepest descent or the minimum rate of change, we can just simply go ahead and flip the sign once we have arrived the value of the gradient, right? So in this case, it's asking for the steepest descent, so we are going to do step 2 and 2.1. So step 2 is gradient of f at 2 and 3. This will give us 3 plus 18 e to the 6. And then 2 plus 1, 2 e to the 6. This will equal to 21 14 e to the 6. And it's asking for the, so that's 2.1, since it's steepest descent, therefore it's negative 21, negative 14 e to the 6. So if we want the value of the value or the magnitude of the maximum or minimum rate of change value, we're going to find the magnitude of f. But this question is not asking for that, so we're just gonna go ahead and say no need to find the magnitude, right? So they might ask you for that. Other questions they might ask you for that, but in this question, we don't need to do that. Step 4, if we want the direction of the maximum rate of change, we can find the unit vector, right, of the gradient vector. Or any scalar multiple of the unit vector also works if it's not particularly asking for a unit vector as the direction. So in this case, we can go ahead and divide by what we just have by 7 e to the 6. We're going to get negative 3 and negative 2. So this will correspond to answer choice alpha, and then that is the correct answer to this problem, right? I don't know if you noticed that answer choice B is the direction of the steepest ascent. So that is the trap that the problem maker has already put down, kind of waiting for many students to fall into. So it's important to be aware, to be very careful when we do these seemingly easy problems. So that's what we have for gradient problems, right? Just find the gradient, plug the values in, and then we can adapt to whatever the question is asking for based on what we have already learned, such as the magnitude of a vector, unit vector, right, or scalar multiples, right? So let's go ahead and tackle the next type of problem, right? So we're going to find the directional derivative of the function as such in the direction of the vector and the point, right? So by investigating this problem statement, right, directional derivative is a big giveaway to tell us that this is nothing, and it's no other than a directional derivative problem. So, right, and other giveaways, right, we also have this, the vector that we want to find the partial directional derivative in the direction of. So let's go ahead and start solving it. So the first step we're going to do is we're going to identify the function, the point, and the directional vector, right? So we have a lot of things that we can work with. So the function is going to be natural log of 1 plus x squared plus y squared plus e to the z, right? That's quite a big function. And then the point, the point is 1, 1, 0, and then the direction vector u is 1, 2, 3. Okay. But look what we have talked. Remember what we have talked about before. What's the special requirement of the directional vector, right? The directional vector has to be a unit vector, right? If it's not a unit vector, we need to normalize it. So the u is going to be 1 over 1 squared plus 2 squared plus 3 squared, 1, 2, 3 equals to 1 over root 14, 1, 2, 3. So that's step one, right? It's a preparation for what we need to do next. And then step two is going to find the gradient of the function as usual, right? So let's go ahead and get on that. So step 2, gradient, right? So fx, fy, fz will equal to 2x, right? So we're just gonna do the power rule first. The power rule of the derivative of the natural log, right? -1, and then we're going to include the chain rule right here, and then everything is the same except the chain rule part. So we're going to have 2y, and then we're going to have e to the z power. So therefore, the gradient of f is going to be this whole one of these guys, 2x, 2y, e to the z, right? So that's not bad at all. So there you go. There's the gradient. So step 3, we're going to plug the point into the gradient of function of f. So to get the gradient in terms of actual values. So the gradient at 1, 1, 0 equals to this whole jumbo will equals to 1 over 4, and then we're going to have 2, 2, 1, right? So this. So let me just go ahead and expand that a little bit for you. So this will give us 1 plus 1 plus 1 plus 1, and then to the negative power. And then we're going to have 2, 2, 1 equals that. So step 4, we're just going to take advantage of the directional derivatives. So directional derivative, gradient of f times a dot product with unit vector, which will give us 1 over 4, 2, 2, 1 time dotted with 1 over square root of 14, 3, 1, 2, 3, and this will give us 9. So 9. So everything in the dot product will be in the numerator, and then we're going to have to collect the denominator, 4 times square root of 14, and this is the correct answer for this problem. I think that's answer choice A. So yeah, so that is all I have for you for gradient vector as well as directional derivatives, right? In many cases, you just what I'm teaching is how to systematically approach a problem, and then to utilize any necessary formula to arrive to the destination. So, and then again, the process, right? The process that I have shown you on the left, it's much, much more important than what I have shown you on the right, because these things on the left, these processes, you can apply them to any problems of the same type. And that's all I have for today. I hope you, thank you very much for watching. I hope you learned something, and then I will see you in the next video.